Loading one model per fine-tuned task wastes GPU memory. vLLM can serve multiple LoRa adapters per request on a shared base model, and load new adapters without duplicating weights. You'll configure vLLM to load multiple LoRa adapters and route each request through one shared base model without duplicating base weights. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Many teams fine-tune a separate full model for each task, and then run out of GPU memory fast. The issue isn't accuracy so much as cost and manageability. If you keep one big base model in GPU memory and swap small task adapters in and out, you avoid duplication and can iterate faster. vLLM gives a small HTTP surface that lets you register and route LoRa adapters at runtime, which makes safe rollout and rollback practical. At a high level, multi-LoRa serving with vLLM is one base model with several small adapter overlays. You decide which adapter to use per request. Think of the base model as the engine, and LoRa's as plugins that nudge the engine's behavior without replacing it. That keeps memory steady while serving many task specializations. We will build a compact demo. Inventory the server, load two adapters, route requests to each adapter, check an allow list so only approved adapters run, and then unload an adapter. That walkthrough covers the lifecycle you need for safe serving. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. This snippet checks which model IDs the local vLLM server is already exposing. Engineers often inherit a running endpoint and need to know whether they are looking at one shared base or several duplicated deployments. The code uses requests get against /v1 models, turns the returned data into sorted model IDs, and keeps URL available for the rest of the flow. That small inventory step is useful before loading adapters, because later changes should add LoRa entries without requiring another base server. The output shows the current visible model count and first model ID, giving us a baseline for the adapter rollout. We now need to bring the new adapters into the server process without restarting or duplicating the base model. This example dynamically loads two LoRa adapters into the same vLLM process. Adapter rollout is where cost and latency problems often start, because teams accidentally deploy another full model just to serve a new task. Snapshot download materializes each adapter locally. Then requests.post sends LoRa name and LoRa path to SSV1 load LoRa adapter. Keep this endpoint behind trusted automation in real deployments, because runtime adapter updates should not be exposed to arbitrary callers. The output shows how many adapter load attempts were made and the final HTTP status, confirming that vLLM accepted the latest adapter registration. With adapters registered, we must send real requests and choose the adapter per call so we can compare behavior. This code routes each request to a different LoRa adapter by changing the vLLM model field. The important shift is that the caller chooses SQL LoRa or class LoRa per request, while the server can still share the base model behind those adapter names. Jobs keeps the routing decision next to the prompt, and requests.post sends each body to /v1 completions with temperature set to 0 for repeatable demos. Max tokens limits how much each adapter can generate. Increasing it allows longer answers, while decreasing it caps latency and output cost. The output shows both adapters return text, proving per request selection is working. Before routing traffic broadly, add a small allow list check. so a typo or a bad rollout does not surprise you. This snippet turns the vLLM model list into a simple adapter allowlist check. In production, adapter names are a control surface. A typo, stale rollout, or unexpected adapter can change behavior even when the base model is stable. The code calls v1 models again, compares served IDs against approved, and keeps the original base model from model IDs out of the blocked count. This is intentionally small, but it mirrors a useful monitor or readiness check before routing user traffic. The output shows how many approved adapters are live and whether anything unexpected is being served. If an adapter performs poorly or causes a regression, you should be able to remove it instantly and confirm the change. This example removes one adapter from the running vLLM server without touching the shared base model. Rollbacks should be boring. When an adapter causes bad answers or latency spikes, you want to stop routing to that adapter without draining the whole GPU deployment. Requests.post calls v1 unload LoRa adapter with LoRa name. Then a fresh v1 models read verifies whether class LoRa is still advertised. That gives the incident path a concrete confirmation step instead of relying on logs alone. The output shows the adapter name and whether it remains live, which is the final lifecycle check for dynamic serving. Mapping this toy flow to a real project is straightforward. Swap the demo prompts for your internal support tickets or domain docs. Plug the same lifecycle calls into authenticated automation and gate rollouts with metrics that measure P95 latency when an adapter is loaded versus unloaded. Those measurements give you practical safety gates before you route customer traffic. In short, keep one persistent base model and load small LoRa adapters on top. Select an adapter per request and secure and validate adapters before runtime changes. Use this when you need many task-specific behaviors but want to avoid full model duplication and the associated GPU cost. And remember one caveat: uncontrolled runtime loads can change behavior. So lock down the load endpoints and validate adapters before rollout. A practical next step is to run this flow against a real internal dataset, say 1,000 recent support tickets, and measure P50 and P95 latency while varying max tokens from 64 to 512. That will reveal the latency cost of longer responses and help you pick a max tokens value that balances cost, quality, and user experience. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.